Hello everyone, I am Dr. Nitin Kumar Saxena. In previous videos, we have discussed the concept of potential energy, potential, potential energy difference, potential difference. How can we find the value of potential at particular point due to a point charge? What will be the value if we have a dipole? And now we will see the other concepts related with this chapter. So let us start with first topic, the equipotential surface. The topic is equipotential surface. You see, from the name it is clear that if you see eq and potential means equal, eq means equal and potential means the value of potential and surface. So what you can say that a surface at which the value of the potential is same equal everywhere is called equipotential surface. So theoretically a surface where the value of potential is equal at every point. So such a surface is called equipotential surface. To understand this, let's see, we have this point charge plus q. Okay, and for this point charge, you see, like if I draw, like if I am saying at a distance of r, if I am drawing a circle at a distance r, if I am drawing a circle, so at every point of this circle, what will happen? At every point, see, this distance is also r, this is also r, this is also r. So on this circle circumference, wherever you go, you will get the same distance from this point charge. And you know, suppose I am saying this point A. So what will be the value of potential here? 1 upon 4 pi epsilon Q upon R. Either you write epsilon or epsilon naught. It doesn't matter because normally we work in vacuum, and vacuum the value of epsilon is equal to epsilon R epsilon naught, because the epsilon is given by epsilon for vacuum, epsilon R is 1. So normally whether we write epsilon or epsilon naught, the same thing. In most of the expressions you may confuse whether I am writing epsilon or epsilon naught, but whenever I am writing epsilon or epsilon naught, I am considering that all calculations are being done in vacuum, right? So if this is the value of potential, so you see wherever you go on this circle circumference, you will get the same value of potential, and hence what you will say that this is the equipotential surface for this point charge. So in this case we can say if I have this point charge plus q, so and you draw this circle, you can draw so many circles, infinite circles you can draw, mathematically infinite circles you can draw. So these all circles are the equipotential surfaces for this point charge. So 1, 2, 3 and so on are the equipotential surfaces for point charge. Okay, this means if I move on any one circle, suppose I am moving on this circle, so does not matter I am at what point, the value of potential at each and every point on this circle will remain same. So because this distance is always same and the formula is 1 upon 4 pi epsilon q by r. So this surface 2 is a equipotential surface for this point charge. Similarly, if the question comes that how many equipotential surfaces are possible for point charge, so there may be infinite. Okay, because whenever we are changing the value of radius, we will get a new equipotential surface. So how many surfaces are possible? Infinite, right? For this point charge. Similarly, if I am saying, okay, if electric field lines are passing like this, suppose electric field lines are going like this, and I am saying this is uniform electric field which is passing from left to right. Okay, so it's passing from left to right, and like if I'm saying we have some, like it's called, like if I'm saying okay, it's not a it's not a one dimensional figure, it's a right, so it's not a one dimensional figure, so you will stretch over here also, so it continuously it is going from every place, right? So you can imagine a wall of the room, so from the wall, from one wall to the front wall, the electric field lines moving. So you see, if I put uh, different walls, different walls like this, so you see, at every point of this wall, you will get a same value of potential. So what you will say, this is a equipotential surface for this uniform electric field, right? So depending on the direction, depending on the magnitude, and depending on the electric field right behavior, you can find the equipotential surface. And the important point is that you will get equipotential surfaces when you have uniform electric field, right, and constant magnitude electric field. Otherwise, the concept of equipotential surface is not possible. So, I hope the concept of equipotential surface is clear to you. Now, let us move on the second topic, next topic, relation between field and potential. Next topic is relation between field and potential. As you know that electric field intensity is given by capital E and potential is given by B. So what would be the relation between E and B? So this is our prime aim, that what should be this relation. Okay, how can we formulate between electric field E and potential B? To understand this, let me have a uniform electric field which is going from top to bottom, right, which is going from top to bottom. In the same case, you can imagine that if you are in a room, then the electric field lines are moving from floor to roof everywhere. So it's an uniform electric field, right? Now I'm saying a unit charge plus 1 coulomb is at point A initially, and now after some time it would be at point B, and the distance between A and B is, suppose, dl. So to get the value of relation between electric field and potential, what I am saying, that a uniform electric field is acting from bottom to top, and we have a plus 1 coulomb unit charge which is initially at point A, Now it will move to dl distance and will reach to point B. So naturally when it will move from this point to this point in this electric field, it will gain some potential energy, right? So if it will gain some potential energy, so what will be the relation between a potential and electric field? That we will try to know through this concept. So you see, suppose I am saying, okay, at the point A we have potential B, and at point B we have potential dB, right? So at the point A the value of potential is B, at the point B the potential is B plus dB. Since plus 1 coulomb charge is moving, so what is the potential energy? So potential energy in 1 coulomb charge when it moves from A to B is at, you know that since the value of charge is plus 1, so potential will equal to the potential energy. I have told you in previous class that the potential energy UA minus UB divided by Q is defined as VA minus VB, right? So if I'm using this, so what I will get? I will get the potential difference is VA minus VB. So V minus V plus dV equals to minus dV. So this will be the potential energy which will be stored in this plus 1 coulomb charge when it moves from point A to point B. Now we have also studied that this potential energy comes in charge by the work done on the charge to bring it from point A to point B. Now we will try to find that what would be the work done on this plus 1 coulomb charge to bring it from the point A to point B. So for understanding this, again you see that if this is a plus 1 coulomb charge, so the force acting on it will be E, because the value of Q is 1. So what you will say? E, because this Q is 1. So this is the force of this coulomb charge, and the work done to bring the point charge plus 1 from point A to point B, the work done is defined as the force into displacement. What is the force? E, and what is the displacement? dl. So what you will say? The work done to bring this plus 1 coulomb point charge from A to B is given by force into displacement. What is force? E. What is displacement? D. L. Right? And from the previous definition, we know that the work done to bring the point charge from point A to point B is equal to the potential energy stored in this point charge when it moves from A to B. And hence we can compare these two expressions, and what we will get? E dl is minus dB. So E will be minus dB over dl. So this will be the relation between the electric field intensity E and the potential difference. So we can say that the rate of change per unit length, the per unit change in voltage per unit length is given by the value of electric field intensity, right? Change in voltage per unit length is given by the electric field intensity. And you see here you see here, like the first point, since here you see there is a negative sign. So what it negative sign shows? It shows that when you are moving an electric field, so your potential value will decrease, right? So the value of potential decrease if you are moving in the direction of electric field. So on moving electric field direction, potential will decrease, right? Is it clear? And the next point, you see that the same concept, if I am replacing point charge from this point to any point in this surface. Suppose I am saying this is a equipotential surface. Here also, we have seen the concept of equipotential surface. So from the concept of equipotential surface, if electric field lines are going from bottom to top, so what we can say, there will be some equipotential surface, and this derivation holds good if this plus 1 charge is at either place on this equipotential surface and moving to either place of the equipotential surface. So what we can say, that the magnitude given by the change in magnitude of potential per unit length will always be equal. So this is the property of equipotential surface, right? So I hope the concept of relation between field and potential is clear to you. So next, move on the potential energy of a system of charge. We have seen that if we have any charged particle, okay, let me clear it, then I'll explain you. So what I am saying, the potential energy of a system of charges. The potential energy of a system of a charges. For we have seen that if we have a single point charge, suppose plus Q1, then what is the value of potential energy? The value is given by UA, because we suppose that we are bringing it from infinity to plus Q1. Now suppose we have the 2-point charge plus Q1 at A plus Q2 at B. So this case we have also seen that in bringing this, what would be the value of potential energy in bringing these 2-point charge at point A and B, right? Now I am saying I have a system of charge, means in place of 2 we have 3, or we can have more than 3. So I'll give you the derivation, the concept. For 3 charged particles, the same can be used for any number of charged particles, right? So I am saying, okay, this is A, B, C, and A, B, C are such that we are bringing these system. Then what will be the combined potential energy of this system, right? So to understand this, let's see, initially I am supposing that, okay, this is the case that we will drive Initially what I am saying, okay, initially we have only bringing first the charge particle A from the infinite. So in bringing this charge particle from infinite, what will be the value of potential energy? The value will be 1 upon 4 pi epsilon Q1 upon, suppose Q1 upon R1. I am saying, what I am saying? I am saying that in general, we are saying that this is any point P. So with reference to this point P, the value is Q1 R1 P. Right? So this is the potential with respect to this reference point P. I am supposing any general reference point P. Now, since this Q1 is placed at point A, now I want to move this plus Q2 charge particle from infinite to point B. So, if I want to move this charge particle B plus Q2 from infinite to B, so it will come at point this in presence of the potential of this point charge. So it has to be like in placing this Q2, we have to work some we have to do some work. And what will be the work done? So work done for Q2 will be 1 upon 4 pi epsilon Q1 Q2 upon R12, right? So this will be the value of work done on this charge particle. You see, here we are assuming that all Q1, Q2 and Q3 are positive. So you see that if Q1 and Q2, if both are positive or both are negative, in both the case we will get this value always greater than 0. If one is positive, one is negative, then we will get this less than 0. So you see, here what you will get when both are in positive, so they will repel to each other. So we have to do some work, right? And if one is positive, one is negative, either positive, either negative, so they have some attraction force. And in this case, we will get the work. So we will work here, we have to do work. And here we will get, right? So this is the difference between the magnet, sorry, the between the like the polarity of the charges, if they are positive or they are negative. So I am saying now, okay, if I am saying similarly, if you have two charge particles A and B, then the work done in bringing them will be this, right? Now see, I want to bring the third charge particle now. So at point C, what would be the value of potential? The potential will be 1 upon 4 pi epsilon. The potential will be at C, you can say like this, BC will be BA plus BB, right? So potential value at C will be the sum of the potential due to A, potential on C due to A plus potential on C due to B. This is fine. So potential on C due to A will be Q1 upon, suppose this is R 1, 2, 3. So I am saying 1, 3. 1, 3 means the distance between 1 and 3. Plus 1 upon 4 pi epsilon. Potential on C due to B. So Q2 upon 2, 3. R 2, 3. Right. So this will be the value of potential at point C. due to 1 and due to 2, right? So if I want to find the value of potential energy in bringing, or you can say the work done in bringing point charge Q3 at point C, what will be the value? The value will be, suppose I am saying this W3 1 upon 4 pi epsilon, this potential multiplied with this charge Q3. So Q1 upon R13 plus 1 upon 4 pi epsilon Q2 upon R23, the whole multiplied with Q3. So the value will be 1 upon 4 pi epsilon Q1 Q3 R13 plus 1 upon 4 pi. Okay, so I'm reviewing what we have done. I'm saying that for making this assembly, making this system, what we will do step by step. First, we will bring the charge particle Q1, then charge particle Q2, then charge particle Q3. First, when we are bringing the charge particle Q1, so there is no electric field. Since there is no electric field, so what we will say that in bringing, so in bringing Q1, the work done is 0, right? So in bringing the Q1, the work done is 0 because there is no electric field. Now, in bringing Q2, when we want to bring this Q2, so there is one potential which is produced by this charge particle Q1 because Q1 already exists. So the value of work done is given by the formula this. So this, suppose I am saying W2. So what is W2? W2 is 1 upon 4 pi epsilon Q1 Q2 upon R12. Right? So we have Q1 and Q2. Now I want to bring third charge particle Q3. So in bringing Q3, work done is W3 and the value of W3 is given here, right? So we have the value of work done in bringing Q1, then bringing Q2 and finally bringing Q3. So what would be the total work done in bringing making this system? The total work done will be W1 plus W2 plus W3 and hence we can say that, okay, hence we can say that in bringing or to develop this system of charge, the work done will be W1, W2, W3. When you will put the values of W1, W2, W3, what you will get? 1 upon 4 pi epsilon Q1 upon Q2 R12 plus Q1 into Q3 R13 plus Q2 Q3, this is Q3, okay, Q2 into Q3 R23, right? So this is the work done, right? And you know that work done in bringing this system is equal to the potential energy stored in this system, and hence what you can say, you can say potential energy is given by the same formula. This is fine. So in this way you can find the potential energy of a system of charge, right? So what you will do, you will bring first charge particle, then what will be the work done, then what will be the work done when you will bring in the second charge particle, and finally what will be the work done when you are getting the third charge particle. And you see here, it is the most general formula. If you have suppose 4 charge particles, then you will get this type of relation for all the 4 charge particles. So this is fine. Now let us see what are the important conclusions from this expression. First of all, you see that what I did, first I bring first charge Q1, then Q2, then Q3. If I do the same thing in any other way, like first I bring this V, Q2, then Q3, and then Q1, or first I bring this Q3, then Q1 or Q2. So the answer will remain same, right? So what does it mean? It means it doesn't matter that which charge particle you are bringing first, then second, then third. The final conclusion, the final result will remain the same, right? So this is independent on the sequence of the charge which you are bringing from the infinite. Also, second thing, like it's also very important, I said that this is plus Q1 charge and this is plus Q2 charge, right? And what is the potential energy or work done for this assembly? 1 upon 4 pi epsilon Q1 Q2 upon R12, right? R12. So you see that the final value of work done depends on the displacement between the charge particle Q1 and Q2, right? In this formula, there is no consideration that how we are bringing this charge particle. Suppose I am saying initially the plus Q1 charge particle was there, and now when we are bringing this charge particle Q2 like this, so we are following this path, right? Now in bringing this from infinity, I am coming like this, or I am saying okay, I will come like this, and finally I am coming at this point at C. So you see, the final value depends on the displacement between the 1 and 2. Doesn't matter from which path you are bringing the charged particles, either Q1 or Q2. So you can say the final potential energy is independent of the path in which the work has to be done to bring this charged particle at this final positions, right? Suppose the next point is the potential energy in an external field. Okay. We have seen the relation between the electric field and the potential. Now we want to see the relation between the potential energy, the relation of potential energy, right, with external fields. If we have any external field, then what would be the value of potential energy? So we have studied it and we are again giving you the value. Suppose potential energy in an electric field. Right? So potential energy in an electric field is same as you know that potential at any point equals to, what is the value of potential at any point? Suppose V, and if charge Q is bringing on this point, so work done in bringing it will be the potential energy. Right. So if we are bringing this charged particle at this point where we have the value of potential V, so the work done will be equal to the potential energy. Hence, the potential energy is given by, what will be the work done? The work done will be QV. Okay. So this we have already seen in previous lecture, but since again the concept of potential energy in electric field comes, so I am giving you the formula again. Potential energy equals to Q times B. Right. Now you see here, what is the main concept in writing it again? If I am saying I have one electron, okay, and this electron is moving in a electric field. Sorry, it is moving in an electric field, right? And due to this electric field, suppose the change in voltage is 1 volt on this one electron, right? This electron is moving in electric field direction. So you know that when it is moving in electric field direction, so we have to do some work because the direction of force will be opposite on it. So we have to, right? So you see that the work done on this electron will be QV. So what is Q? 1 electron into 1 volt. What is the value of 1 electron? So much joule. So this is the concept of 1 electron volt. So when an electron comes in electric field, so due to this electric field, it will get a potential, right? And due to this potential, it will gain some energy, and since it is gaining some energy, so what is the value of this energy? 1 electron volt, and this is the value is normally used when we study the concept of atoms, the concept of nucleus, etc. So the energy keeping by 1 electron and moving for 1 volt, the potential, if it has a potential difference of 1 volt, so what is the energy stored in its electron? 1 electron volt, and the value of 1 electron volt is given by 1.6 into 10 to the power minus 19 in joule, right? So I hope this is enough for this lecture. I finished this lecture at this point. Thank you very much.